Okay, hello everyone, and welcome back to my YouTube channel. I am recording this video because a few weeks ago somebody was asking me about a model for AGC. AGC means an automatic generation control, okay? That is one of the controllers used for frequency or frequency control inside a power system, okay? And this person was asking me about the model of the AGC using the DIgSILENT PowerFactory, okay? And then I decide, okay, we have a very good contribution, and not much people know about that, okay? Let me tell you, in 2013, 2014, I have a meeting with my friend, very close friend, and collaborator, Jose Luis Reda. And I don't remember what conference, but we were together and we were thinking about writing a book of applications using PowerFactory, okay? Application for power system analysis using PowerFactory. At the very beginning, we were a bit selfish and we tried to write the book by ourselves. But then we decide why we need to write the book by ourselves if there are many good and talented people around the world with very good skills, proof skills, serious skill about the DIgSILENT PowerFactory. And then we decide to write the book, and finally in December 2014 we published the book. And today I am doing this video not because the book. I just want to tell everyone that chapter number 7 of that book is dedicated for the modeling of automatic generation controlling power system, okay? And that beautiful chapter is one of there are many beautiful chapters, but this one is quite special because it's coming from people from Ukraine, and especially very close friends right now, Anton and Pavlovsky. They are working. Pavlovsky is the CEO of the DMCC engineering in Ukraine, and Anton is also in Ukraine over there, okay? They spend quite good time writing this chapter, and I know that probably they will be mad because I am presenting their names and affiliations, but we need to present respect and show the original person that they create this chapter, okay? Well, what I will do now is the plan is the following, okay? Initially, I want to show you some a short introduction about the book, okay? It's not for commercial purposes, okay? It's just because I noticed that people, they don't know about the book, and the book is still quite interesting, okay? To be honest, I am really proud about this book. Jose Luis Reda and myself, we talk with many people around the world. There are around 50 countries represented in this book. People coming from everywhere, from Asia, Thailand, Chile, Ecuador, Ukraine, India, United States, United Kingdom, etc. Okay, more than 50 experts, and right now some of them, they have very good positions around the world. I know that few of my colleagues will be mad that I am showing the faces over there, but I would like that you understand that they are real people behind this book, okay? People with a lot of knowledge and people with very good credential, okay? Serious people, okay? Well, we wrote this book. The book has 20 chapters. Today I will be just talking about the chapter number 7, that is the AGC model, okay? For disclaimer, Jose Luis Reda or myself, we don't have any commercial relationship with DIgSILENT PowerFactory. However, I will say that DIgSILENT PowerFactory is probably our best collaborator, and they are quite good and supporting to us. Okay, in fact, I am really proud that in 2014 Dr. Martin Schmiek wrote the foreword for that book. Okay, and for me it was very nice that he started the forewords with a very beautiful introduction telling about the origin and the first client of the DIgSILENT PowerFactory. And Marty's talk about the first customer, official and registered user of the DIgSILENT PowerFactory. And at that time, the book was published in 2015. 27 years later, they still being a user of the DIgSILENT PowerFactory. And the forwards is amazing, and he recognized our effort over there, all the authors creating amazing and impressive demonstration about applications, power system applications using PowerFactory. Okay. Well, but I don't want to sell the book. It's not my business. I would like to talk more technical stuff. I would like to talk about the chapter number 7. Sorry, Pavlovsky and Anton. I am taking your chapter, and I am probably not the best presenter. I think I will invite you to do the video later. But what I will present is just very short introduction, very quick introduction about chapter number 7. Okay, chapter number 7 is related with the modeling of automatic control generation. Okay, and before jumping into the details about this, I would like to run a very short introduction. Okay. Something that you must understand is that power systems, we need to keep the balance between generation and demand second by second all the moments, okay? Because the generation and demand, when they are in balance, when there is a balance between generation and demand, the rotational speed of the synchronous machines is constant, and as a consequence, the frequency is constant, okay? If we are in a real power system, the frequency is changing, but it's inside a very small band, okay? The situation starts to be complicated is when we have a system frequency disturbance. For instance, we have the sudden disconnection of a big generator. We have a generation deficit. I mean, they are more load that active power provided by the generators, and as a consequence, the frequency drop. That is what is happening here. At t equals 0, we have what we call the power imbalance. We have a deficit of generation. The machines start to slow down, and because the machines are slowing down, we have a drop in the frequency, okay? The very first drop is probably very important. It's quite fast. I will discuss what is happening there in few seconds, okay? Then there is a very important point here, that is the minimum frequency. The minimum frequency is extremely important because the minimum frequency must be above what we call the under frequency load shedding, okay? We want to stop and avoid any kind of load shedding. Then there are a few controllers inside the power system trying to recover the frequency, and those controllers, they receive the name primary controller and secondary controller, okay? And at that moment is where we can identify that if everything was fine and the power system have enough capacity to recover the frequency, okay, the power system after the disturbance, or the primary controller will try to stop the frequency down, and the frequency probably will reach what we call a pseudo steady state frequency, and then the frequency will be below the nominal frequency. And that is the moment when the secondary controller starts to jump in and recover the frequency to the nominal frequency, okay? That is basically a very generic and very basic description about the frequency control processes in a power system, okay? I didn't use a specific terminology from American or Europe because the YouTube viewers can have and can be located at different locations, and they can be confused of different terminologies, okay? However, what I want to say is at the very beginning, when we have the system frequency disturbance, and we have the first drop here in the frequency, to be honest, the synchronous machine is quite amazing, because automatically the synchronous machine can feel, I will use a very interesting word, can feel the power deficit, and automatically, I mean, it's something natural, the machine try to change the rotational speed, releasing kinetic energy from the rotor, and that is what we call the inertial response, okay? It's something that is natural from the synchronous machine directly connected to the power system. It's trying to reestablish the balance between generation and demand. It's when the machine starts to release the kinetic energy, and because it's releasing kinetic energy, it's slowing down, and the frequency goes down, okay? However, we have several controllers, frequency controllers inside the power system. One of them is the governor action, okay? We have this controller that is, in theory, the controller is trying to reestablish the balance between generation and demand, okay? Try to make the machine to stop the frequency down, try to stop the machine to reducing the rotational speed, okay? That is the governor. And then, when we have the governor has some time constants. That time constant could be related with several seconds, okay? And then we have here the process where the frequency must go back, okay? And that is the secondary controller. That is the Agc. That is the topic that I will be discussing right now, okay? The Agc is basically a controller that is working in a time scale larger than the classical governor action, okay? After the governor action, after the frequency reach some pseudo steady state frequency, the Agc jump in and try to recover the frequency, okay? However, how is doing that? It's quite important, because it's quite important that you must understand that. When we have the inertial response, that is something natural that is coming from the inertia of your machines, okay? That is something that depends on the size of your rotor and the kinetic energy stored in your rotor. The governor action depends on several parameters. One of them is the time constant related with the controllers, but also some gains, okay? However, this is a controller, okay? And this controller has a limited time space for action. And then the secondary controller, frequency controller, is basically dedicated to come back the frequency, okay? To do that, basically what the Agc is doing is changing the reference, the active power reference for the generators, and increasing the mechanical power in order to increase the active power, and the machines accelerate and start to come back to the rate frequency, okay? That is basically a very short and basic introduction about Agc. However, if you are watching this video, it's because you know what is an Agc, and you just want to know about the model inside PowerFactory, okay? Okay, something that you must understand, there are at least 3 different layers. There are 3 different frequency controllers that you can identify in an electrical power system. I told you about inertial response. That is natural, that is not a controller, but the governor is the controller, the primary controller. Then we have the secondary control that is basically related with increase the power generation in order that we can recover the frequency. And then there is a tertiary controller, probably more than that is mainly related with very long time scales, but is basically for economic purposes, okay? Here there is a classical representation. The classical representation, you can see that the primary control is a local control, is acting directly on the prime mover of the generator, is acting on the signal that is, for instance, opening a valve to release more steam, or opening a gate to release more water for the hydro turbine, etc. Okay, but it's a local primary control. Then we have the secondary control, and the secondary control is doing the action for the Agc, the automatic generation control, okay? And it's basically related with some errors related at the power interchange inside the system. The secondary control is slower than the primary control. Time scale of several seconds. It could be even few minutes. and typically is a wide area system, okay? It's related with very low speed and is spread across the system, because basically what it's doing is sending references signals to the primary control in order to recover the frequency. And then we have a tertiary control, and they are more that they are basically slow and with some characteristic related with economics, okay? I will not go in that detail. This presentation can be downloaded from my ResearchGate. If you want to know more about frequency control, please go to my ResearchGate. This is a presentation that I ran a couple of years ago in Spain. However, the link is over here. You can go to my ResearchGate and you can download the presentation, and you can read and learn more about frequency control. I don't have time here in this video, okay? Now, what I will do is I will discuss the chapter number 7, but to do that, what I will do is I will go to DIgSILENT PowerFactory and see the models and explain the model, okay? Okay, let's jump into DIgSILENT PowerFactory, okay? Now we are in DIgSILENT PowerFactory, and this is the automatic generation control. This is the project, the DIgSILENT PowerFactory project that was created for the chapter number 7. Okay, every single chapter in the book, in our book, there are examples that you can follow step by step. You can download the samples, you can run the samples, and you will get the same answers that our collaborators presented in the book. Okay, this is a very pedagogical book. Okay. Okay, but Anton and my colleague Pavlovsky, they create the AGC model, and they include an example, okay? They include the IEEE 14 BOSS test system. That is the beautiful 14 BOSS test system, IEEE. However, as you must know, the classic IEEE 14 is basically for lot flow. However, they did a very good job. They include some generation control, some prime movers, some governors over there, okay? As you can see over here, let me show you. This is generator 1. There is a generator model over there. Generator 21, generator 22, and generator 32, okay? However, when we are working with AGC, it's because we assume that we have several power plants inside the power system. As you can see here in brown color, there is a power plant number 1. Here is the power plant number 2, and this is the power plant number 3, okay? What is doing the AGC is, if we have a sudden frequency disturbance, there is a power imbalance. For instance, we have too much load. Well, the AGC will add after the governor, and it will take care about the frequency of the system, but also it will take account if there is a pre-scheduled net interchange power inside the power system. And for that reason, Anton and Pavlovsky, they divide the IEEE test system in 2 areas. I believe you can see here IPS1 in this left-hand side and IPS2 on the right-hand side, okay? What does it mean? That this IPS1, that there are some loads, transmission lines, and so on, that represent one area inside the 14 BOSS system. And everything on the right hand of that blue line over there, that represent the power system number 2, okay? And the net interchange is basically the power flow that is moving from those transmission lines over there. You can see that they are one transmission line, and the name is 122. This is 121, and over here we have the overhead transmission line 15. Okay. Okay. What I will do is the following. What I will do is basically I will include a system frequency disturbance. And the system frequency disturbance will be a sudden load increase in the load number 1. Okay? I will suddenly increase the load at load number 1. I will run here initial conditions, okay? And then let me check. I have another disturbances here, but let's see this one. Yes, this is a step increase. This is a step increase of 25% at the load number 1, okay? That is happening at 0 second. You can see here, load number 1, 25% increase, and that is happening at 0, okay? That is the only disturbance that is over there, okay? The other two disturbances are out of service. They don't take in account, okay? Okay, now, very basic question. What will happen if we have this sudden disturbance and there is not AGC action? Well, it's very simple. It's what's happened in every single power system that you simulate without AGC. If the system has frequency stability, the system will develop some recovering forces, and the frequency will recover a steady state value, but that frequency will recover at a value that is different to the rate frequency. Because you must remember, if we don't have AGC, the frequency will not be able to recover, okay? Give me a second and I will go back to my presentation. If I go back to my presentation, if we don't have AGC, the frequency fall down, reach a minimum. If the system, if the frequency is stable, then the frequency will get a steady state, and that steady state will be below. It will be below the rate frequency. It will be below if we have a drop. You must remember megawatts per second, and that frequency will be down. Okay. Okay. Now let's come back to PowerFactory. Okay. What I will do now is, sorry, Anton and Pavlovsky, what I will do here is I will check your controllers and see, okay, I put out the service, the AGC. Right now, there is not AGC in this power system, okay? Because I want to show you what is the response, the system frequency response without the AGC, okay? Now, let me minimize here. What I will do is just run initial conditions. Then I will run the simulation. And let's see what is happening. Okay, we have here, we have initial conditions. We simulate everything was fine. Okay, let's come back to the system. And I will go to the, there is a plot here for frequencies, okay? Okay, look over there. If we have a system frequency disturbance, in this case was an increase on load number 1 of 25% at t equals 0, the frequency will go down, as you can see over here, reaching a minimum frequency. There is a minimum frequency over here, 49.9 hertz. And then after a few seconds, let me run a bit longer simulation. Let me run 100 seconds. Okay, after 100 seconds here, the frequency is reach a steady state, let's say a pseudo steady state, and the frequency here is 49.948. Okay, as you can see, the frequency is below 50 hertz. Okay, I know my colleagues Anton and Pavlovsky, the IEEE system was basically 60 hertz, but they converted into 50. The IEEE 14 bus bar is American test system, but they converted it into 50, okay? Rate frequency here is 50 hertz, okay? But there is not AGC action, okay? And let me see something here. Okay, what I want to show you right now is what is happening at the interface. What is happening in the interface, at the interface, is that initially we have a power. Let me see the power. Let me zoom in here. Initially we have a power that is around minus 90.2 megawatts. And then after we have the disturbance, the active power at the interface, it's minus 64, okay? Okay, what is happening here? Let me come back here. Initially, we have power going from this generator here in this way. And then we have power going in this way, okay? But then when we have the sudden disturbance, there is an increase on the load power here. And that is the reason that the active power transfer is reduced, okay? Because of course, this generator need to cope with the new power, local power, okay? But now let's see what will happen. Let me show you, I forgot also here, you can see the, okay? Here you can see what is happening in terms of active power, okay? But what I will do, because we are probably 25 minutes, and you can read more details about inside the book. What I want to show you is that they develop a proper AGC and is properly working, okay? What I will do is initial conditions, okay? Now I will go and I will enable those AGC, okay? What I will do here is go in and activate the AGC, okay? And now what I will do is run a longer simulation, let's say 300 seconds. Why I am running a longer simulation? I am running a longer simulation because, as you must be aware, the time constant related with the AGC, they are a bit longer, okay? And if you go back here to the frequency, and let me increase the size of this, what is happening now? Okay? What is happening now is, if you look here at the very beginning, we have the same situation. The frequency is going down. The frequency is going down. It's oscillating. It's reaching some pseudo steady state frequency. Okay? You must remember it was around 49.9. Okay? But if you see the full scale, you can see how the frequency is coming back. The frequency is coming back to 50 hertz. Okay? And that is the proper action. That is the proper action of the AGC. And right now you are saying, okay, why this guy start in this way? Well, because first I want to teach you what is the basic idea of the AGC, and to show you that the AGC is working. The first simulation was without AGC. You can see that the frequency is still below the rate frequency. Then I activate the composite model, that is the formal name, the composite model, and all the DSL are working. And now we have the full AGC action, and you can see how the frequency recover, okay? But now the most important thing is, okay, how do we do that? Well, Anton and Pavlovsky, they spent a couple months doing this. And when they did, what they did is, basically they use DSL, and DSL is basically the name or the acronym for DIgSILENT simulation language. If you are familiar with DIgSILENT PowerFactory, you must know that DSL is the language that we use inside DIgSILENT PowerFactory in order to create dynamic models. And those models can run inside the RMS simulations and also the AMT, okay? But here what you can see is basically one of the frame. Remember that when we are using DSL inside PowerFactory, they are like different type of objects. Some objects, they receive the name frame, and some others receive the name block definition, and then there is the interface with the user, and that is the DSL, the element DSL, okay? Over here, what you can see is that we have some measurements. We have 3 measurements because we have 3 transmission lines. We have frequency measurement because the AGC must take care about the frequency control. And those signals, the power flow together with the frequency, they are going to the main controller, and that is the AGC. Okay? And then we have here what we call the Agc controller. The Agc controller is basically taking the frequency, okay, and using a PI controller, all of you must know that they are using a PI controller, and this PI controller is providing the reference for the Agc. And finally, here we have the brain of the Agc controller, because when we have the full PI controller creating the reference, those reference must be sent back to the generation unit in order to increase the generation and recover the frequency to the rate frequency. Okay? If you are following me, probably you are okay. This is a lot of things behind. Yes, this is one of I'm really proud of Anton and Pavlovsky, because they create a very beautiful model. Okay, and it's a real model and it's working. They demonstrate that it's working. But coming back on the demonstration, what I will do here is coming back again to the system. I run the initial conditions, okay? Then I execute the RMS simulation, okay? And we run 5-minute simulation, and here we can see the frequency, okay? The frequency is recovering. But how the frequency is recovering? Well, because the generation units, as you can see over here, some generation units, the active power suddenly increase during the transient or decrease depending on the location, okay? Here you can see some of those units, they are, some of those units, we are reducing the rotational speed in some units, and as a consequence, the active power is changing, okay? Okay, you can see here, initially we have a sudden change in the active power of some generators. Remember, that is related with the location inside the power system, the relative location between generation and the disturbance, and also the synchronizing coefficients. I will not go there with that kind of explanation, but that is the natural response, natural network inertia response of the system. But then the controller jump in, and as you can see over here, this generator is changing the reference, and this generator is increasing the power, the generator number 1, because the load change happened here, and generator number 1 is responsible inside that area to take care about the power imbalance. And the other generators located at the power plant 2 and the power plant 3, then, because they are in the other side and we want to keep here the control, well, this generator must assume the power imbalance, and then the active power must be reduced on those generators, okay? Here, I will stop this explanation. I think it's a very good time that if you have any question, please contact the author of this chapter, okay? Probably they will be mad, okay, about me because I will do this, but okay, let me show you here the following, okay? You can find the book on Springer. The book has been available since 2014, okay, and you can download from there. You can buy the chapter, okay, and as you can see, this chapter has been quite downloaded, at least 4,900 downloaded, okay. And if you need to contact Pavlovsky or Anton, I know that they will be mad of myself because I am presenting here the LinkedIn, but they have Pavlovsky is the CEO of the MCC in Ukraine, and here you can see Anton. Anton is another very good guy in terms of the power system modulation, okay? And this is the LinkedIn website. This is the LinkedIn website for the MCC. I am really proud that early this year I have the opportunity and I visit them in Ukraine, in Kiev, and we have extremely good conversation with them. They received me over there. They surprised me with the book, and it was quite amazing experience. Okay. Finally, if you have time, please go to my research gate, and at my research gate, you can go to presentations. And let me go to presentations here. And presentations, there are quite a few over there, but the one that I talk about is here. Yes, is the section number 3, system frequency response. And over there you can get all many good concepts about primary frequency control, secondary frequency control, AGC action, and so on. Okay. At this moment, what I want to do is basically close this presentation and say thank you to all of you. Please feel free to call to email Pavlovsky or Anton Steliuk if you have any question about modeling of automatic generation control. Okay. Also, if you need any question, please feel free to email me. Okay. I didn't cover here the DSL modeling because it's something that requires more time. Okay. And sometimes it's better that you can read the book by yourself. You can see the models, you can see how the initial conditions and all the description about the models. Okay, everything like that is included in chapter number 7. Okay. Well, I would like to close this video saying thank you very much to all of you for watching, and in a few weeks we will have more surprises about PowerFactory modulation and simulation, and hopefully we will have quite good of the collaborators. We have here more than 20 chapters in this book, and we have one more book in Smart Grid using PowerFactory. And there are a couple more books coming very soon about protections and about power electronics. Okay. Thank you very much for watching this video. That's all. Thank you. Bye now.